So with that, please welcome Julian to the AA.
Thank you, and thank you for welcoming me here. It's already been a very nice 2 days at a very different school to the ones that I've visited so far. I've really enjoyed it. And I'm just going to talk a little bit across the different kinds of projects that I've been involved with between practice and academia. These were things that always overlapped in my time. I founded the practice very early on when we were working as freelance engineers on the project that you see at the top left. These are the Medina Piazza shading umbrellas in Saudi Arabia. And when we did the structural analysis for it, we kind of founded the practice to just have a bit of backup, and then did the PhD, and kind of the practice was growing at the same time. And then when I finally finished the PhD in 2013, we said, okay, now we'll just give it a shot and see if there is this field for us engineers who are kind of wandering the worlds between research and practice and looking for new challenges in what we can find there. And in that sense, it's always been a kind of a search for creativity and a search for finding ways of collaboration with architects, with other researchers, other engineering disciplines. I'm just going to reflect a little bit on that, of what we've encountered as problems and where we found maybe some first solutions in the last couple of years. And when I talk about civil engineering, I think it's important to highlight that our discipline is actually very young. So the civil engineer as a profession is barely 100 years old. And it used to be that we had architects who were masters at building and who were basing structures on intuition and on experience. And so we see, especially in these amazing large span structures, you see a lot of heritage of engineering that was done that with today's knowledge of engineering doesn't actually make a lot of sense, because it's based on empirical methods, on tests, and on seeing that things hold, but maybe not quite fully understanding why they hold. And this 200-year-old structure at the Gare de l'Est in Paris is kind of a nice example for it. I think lots of people sitting in this room probably passed under it, and you've seen this kind of cable net structure that's bracing these arches. And there's at least 3 overlaying cable tension systems that all by themselves could do the job. And in the way they're overlaid, they actually don't really make sense. But this thing has been standing, and it's perfectly standing. It actually looks really nice. And it kind of makes you think about why, at the point when we founded our profession and we started relying on things that we could calculate, that actually took away a huge amount of creativity in structural design per se. And this had a very big influence from engineers in the railway industry. So the railway industry really were the people that had to build large span structures for their bridges and their big railway stations. So people like Gustav Eiffel, they were actually coming from this industry, and they founded a theory that made it possible to predict the behavior of their structures. And this prediction, this calculation of understanding how the forces travel through a system, what kind of reaction forces they cause, and then understanding how big do I need to size a member, that led to a whole typology of structural systems that we would build our systems with. So there were arches, there was 3 hinged arches, and there was frame structures, all in a way that we could describe them and in a 2D, very easy fashion calculate them. And we're kind of at a point now where today's computation should enable us to leave all of this world far behind, but we're still in this kind of transition phase where we're trying to understand if we can let go of things that we can calculate by hand, how do we then understand what an efficient structural system is? And it's quite interesting that actually not long after this time, it was again a structural engineer, Konrad Zuse, who actually built the first computer. I think a lot of people don't know that this guy was actually a structural engineer, and his motivation was that he said the kind of mundane part of structural engineering, he found it really boring to calculate all of this, and he wanted to compute this and make it automatic. So that was actually one of the initiatives to actually build a computer to make structural design automatic. Today, we're obviously, we've left this long behind, and we're now in a position where we can use modern engineering software like finite element methods or other methods which allow us to not only take a structural system and then break it down into an abstraction and slice it into typologies that we can calculate and then say, now I can perform the structural engineering on an abstract model. No, today we're actually able to take the entire structural system, three-dimensional, limitless in the geometry, and perform analysis on it, and not merely feedback data into the system in terms of sizing, but also influence the design based on our calculations. But this kind of leads to a position of the structural engineer which actually makes work almost a little bit more difficult. It was kind of comfortable when we could break down things into slices and say, if we want to build this, we need to build a frame. Yeah? The spans between the frames are X, and then you just slice your structure and off you go. So now everything is seemingly possible, right? We can just take any model and calculate it. But then what is the basis to design something meaningful, something sensible, something that actually works? And I find it kind of interesting that we're at this point in structural engineering, but when it comes to the construction drawings themselves and to the programs that we use to bring the large structures onto site and onto fabrication, we're actually still relying quite a lot on the traditional systems of cutting our geometry into slices and just breaking it down into something that we can handle. So this project by Zaha is probably known to many of you in Korea, the DDP, and it's an amazing piece of architecture, and it's kind of almost ironic that Tekla, the BIM software, would advertise this and say that Tekla, the software, made the seemingly impossible possible, right? So this is the big slogan on their homepage. They say, we're now able, with our software, to make something that you supposedly can't build, we can make it buildable. But if you focus into it, you see that actually there's nothing terribly innovative about it in the way the structural system is laid out to come up with a new way of answering the questions that we are being asked by architects. And this is not a criticism per se to whoever was on this project, because we just simply don't have the tools. And once you have to design a project of this size, you can't sit down some creative students and just script something fancy so you can shoot out a nice thing that we do at university with our small pavilions. This is massive amounts of steels, timelines, and everything. We just don't have the tools to give the answer. But we have to rely on these softwares, because breaking this down by hand and drawing this by hand, let alone bring it down to shop drawings or whatever else, just simply wouldn't be possible. So there's this kind of promise that we say, BIM, building information technology, this is going to be the future, and this is going to make us all much more efficient, and we can collaborate. There's this kind of promise in BIM that we use to communicate individually between disciplines. BIM creates a central information model which stores the information, and then we communicate across this model, like you see on the right-hand side. And there's this kind of promise that this is going to make us all more efficient, and then we can build much faster, much more reliable. And then the big promise is always that you have then less legal cases within your structural design process. And we are actually kind of there. Yeah? If we build something fairly standard, this is a hotel that we built in the office, and it's amazing to see that today we can build a multi-story reinforced concrete structure of some complexity with just 1.5 engineers in an office. Bring it down to the reinforcement drawings, everything just handled computationally, and in this case, actually going as far as running it off of one single BIM model between the architects and the engineers, and reaching some efficiency in that, and being able to handle such a system with just a few people and in a very short time span. On a side note, this doesn't mean that we're making more money. Yeah? So this is kind of also always the question. If this is making us speed up, if this is making us seemingly more efficient, none of us in the industry have experienced that we've become richer because of that. And we're just doing more, and we're just doing it faster, but we're not really, hugely profiting from that. Because at the same time, the prices are dropping, and at the same time, there's other bits of work coming in that we're not necessarily being paid for, which, just shift the interest. So this is kind of the status quo where we're at. We can combine three-dimensionally the models that we use in structural engineering with the architectural models, and then based on this model, we can bring data towards the architectural design, towards the construction side, and towards our engineering models. On the construction side itself, when it comes to this kind of medium-sized structures, we don't really see any impact of that. Our building technologies, it's all still fairly traditional. So as a result of that, there's this amazing statistics that the German ministry has recently published, where they showed that whilst all other industries in Germany have gained productivity through digitalization, the building industry, which is the blue line, has maintained pretty much the exact same productivity in terms of hours spent per outcome and money you gain. So this is kind of almost a bit scary, right? And that's kind of what I'm talking about. We have these tools and we have this promise that BIM is leading us into this world where everything is becoming much more efficient, but apparently industry is not reflecting this. This has got to do with lots of reasons. It's got to do with the fact that we're only just at the beginning of this digitalization. We're learning to work with it, and we will see new data in the next years where we probably maybe see a trend towards more productivity. But we have this inherent problem of building prototypes, facing completely new challenges with almost every project, and handling a vast amount of individual disciplines which have to be coordinated. And in this setup, it's just not the same setup as building a car where you can automate everything and kind of streamline it to the max profit. So the question is, if there is this promise and we apparently can't handle it, if there's this way that we can now construct things and analyze things, but we're kind of finding it hard to bring it to the side, what is the missing link? What are we missing here? And I totally don't have the complete answer. I'm just seeing kind of moments where we have found ways of kind of tackling exactly this problem in some detail approach. So to kind of highlight what I'm going to talk about, I'm going to pick again a project that I really like. It's the museum from BMW in Munich. Corp Himmelblau designed this. And you can kind of see this trend, right? We're all very familiar with this kind of architecture now, and we find it actually very easy to design something like this. Whilst some 25 years ago, it was actually a real challenge to design something like this in the CAD software that we had available. Today, I would kind of say any undergrad student can pick up Rhino and make a grid shell like that, right? Because you just have the plugin and boom, you go. So it's just super easy to do. And that also means that we just do it, right? We don't spend too much time thinking about the consequences of designing something like that. And then you have the structural engineering software, which you see in the center. And we're also at a point where we can do this really easily. We just pick up the Rhino model. Now for every other engineering software, you already have a Rhino plugin. So you don't even have all this transferring data problem. You just pick up the geometry, perform structural analysis on it. And I would say with today's software, doing structural analysis on something like this requires far less engineering knowledge than doing hand calculation on the bridge that Gustav Eiffel built, which I showed in the beginning. There's also lots of dangers involved because you might not know what you're doing and you might not be able to interpret the results, but just the action of doing it and doing an analysis and achieving a result, whether you'll be able to interpret it or not, has become almost dangerously easy. And then comes the moment where we're to build it. Often in the mechanics of how these things are handled, it goes into tender, and then maybe some totally different people have to handle the project. Then we have to break it down into something that we can construct with the methods that are available today. And the results of that are often something like this, where you can really see that we have these traditional methods, especially in steel structure, how to join things and how to do that automatically. But when we bring in the complexity of geometry that we are able today, there seems to be a kind of break. There seems to be a moment where I'm not sure whether this is the best answer to build this. And it is actually provingly actually a fairly expensive answer too. And this is what I want to talk about a little bit in the next project. So to summarize this thought, we've developed computationally aided design towards computational design, which means that we're not using the computer as a replacement for the drawer, but we're using it generative. And we've been able to use computationally aided engineering towards really hybrid approaches. Yeah? We can simulate, I would say, almost everything. But we really haven't tackled the part of the construction side, the part of the shop drawings, and the part of the detail design to an extent that we can really truly handle the complexities that we're generating in the first two software packages. As a young office, this is kind of something that you can do almost as a strategy when you start with a young office. You often are able to pick up projects in the later design phases. For us, when we were still young and small, it wasn't really possible for us to collaborate with big architects on big projects. But we worked a lot with the building industry that won tenders and that took us to optimize the system towards fabrication. So this was kind of our learning ground for the first 3-4 years in our practice, that we really collaborated with industry, and we were there to optimize the designs towards fabrication. So this was a very important learning ground where you then can also learn to judge what you can still generate in terms of the performance of a system. So this is kind of what this project speaks about. It's a 45-meter span grid shell structure clad with ETFE cushions. And it's this kind of classic thing, very easily designed like that, fairly formal. It's not an efficiently designed shell per se. It's a form. It's actually an entrance building to a dinosaur park, and they have this idea of these splitting cells and eggs. So it's actually fairly formal. And and you can just imagine how easy it was to model something like this and use some Rhino scripts, and then you get a mesh on it, and then you have your grid shell, and you can do the structural design, and you're done. You know the sizes, you know the masses, but you've left the project with a huge impact on industry because not a single node in the system is the same, and you get a lot of angles where the angles are so steep that it's kind of the tubes that are building the node are totally intersecting. So it turned out that the budget was totally blown in the project. They were getting prices that totally blew the budget, and so it got into a second tender phase where people were asked to come in with alternative ideas. And at this point, we entered the project, and we brought in this idea, and this is very much based on the research that we did at university, how we could design a steel node in the same fashion that we were using timber at university to break it down into 2D processes of milling or in this case, laser cutting, and enforcing all information into the pieces that we're cutting. So we don't need shop drawings, and so we don't need any kind of dies that you need to construct a node when you weld it. So I'm going to talk a little bit more about the node, but the basic principle is that you have the degrees of freedom in terms of the rotation of each arm, which is organized by these swords, which are attached to the end of each tube. You have the angle at which they're coming into the node, which is organized by the holes and the cogs of these swords, which are connected like this. And then you have the angle parallel to the normal direction of the node, which is just simply the cutting pattern of the sword itself. So it just becomes this amazing puzzle that you need to be able to put together. And then you can put a lot of thought into, if a piece of steel is on the laser, what additional information can you put onto the piece of steel so you're actually handling it without any shop drawings. So there was a positioning numbering system that would say in the last 2 digits in decimal at what distance they needed to weld the secondary part on the steel. There was a kind of laser marking on the steel that organized the direction of parts. And you kind of break it down until you're sure you can handle this entire thing without a single printed drawing. Because then you can just send it from your computer to the machine and into the manufacturing and onto the site, and then think it all the way to the end that on the site it's also easily erected, it's sorted in a way that they can pick up the parts very quickly, and so on and so forth. So kind of what we're doing in small with this, en vogue pavilion structures that we're doing across all the universities at the moment. It's kind of always the same story, right? We're designing a detail that's kind of logic in itself. We're now calling it the digital detail because it's not only digitally manufactured, but it's also organizing its own manufacturing and assembly. Interestingly, it's actually structurally also performing very well. So the top node is what was put into the tender, a very classic connection that you would bolt together. To hit the angles correctly with a tolerance of less than 1 millimeter or less than 1/10 of a degree, which you need in such a shell, you would have to laser cut pieces of steel that give you the angles. Then you slide in the vertical pieces of steel and weld them. So ironically, you're using modern digital technology, but not to build the node, but just to help build the node. And in this case, we're using the laser to build the node, right? And it's actually pumping up the geometry to some structural stiffness where this very node where you're connecting 7 arms, in our case, only weighed 82 kilogram of steel, and the original one was almost 120 kilogram of steel. If you go times the almost 400 nodes in the system, this is actually a significant amount of weight. And even more in terms of cost, the top node had a total of 2,900 high-strength steel screws throughout the project. And this node, which is only clamped together by one central bolt, because it's a form-fit connection, the bolt is not used to transfer forces, just to lock things in place. It's only 260 bolts. So right there, you're already saving close to tens of thousands of euros just in bolts. So it kind of breaks down into something that finds efficiency in saving weight, in saving manufacturing time, in saving assembly time, and also in saving parts. And the drawings themselves are not drawings, they're just explanations. They're just explaining with some very basic Excel sheets. Quality management is super important, so they need to be able to sign something, right? If something goes out of the factory, they need to be able to sign off that they've checked the measurements. It's something that we had to learn as well. They need a piece of paper where they can put a signature and say this measurement is correct. So we printed out pieces of paper with length of the beams and showed them where to measure them, and then they could sign that off. And yeah, so you kind of see it's basically a system of explaining which part goes where, and then the part itself finds its way through the position numbers. For the engineering of it, it was kind of interesting that we were faced with actually 2 challenges. For one, we had to filter out of a massive amount of data, the results that we needed to actually analyze this node, and then go into a hand calculation of the nodes so we could very quickly script a way to filter out the nodes that are decisive for our system. Because this is also kind of a result of computational engineering, that we now, in our software, we just automatically combine all the load cases. And you combine wind with snow and all the different directions and the different partial safety factors. And you end up in such a project with 92 load cases. So you go 92 times 400 nodes, and then you're trying to filter out what you have to do. You're certainly not going to calculate 400 nodes with 92 load cases. It's just way too long. So this kind of makes us go back to Eiffel and learn to hand calculate things so we can really fastly script them. And it makes us go to some really profound FEA coding so we can actually simulate what this form-fit connection does. Because nowhere in the Eurocode is there a connection with tooths that are grabbing into each other. But by Eurocode, we're allowed to simulate. Interestingly, it actually says in the Eurocode that you're only allowed to do this if you can prove experience, which brings you back to academia. If in your PhD you've done this, and you can just give them your PhD and say, yeah, I know how to use FEA. And you know, it's not a joke. There was a third-party proof engineer which was seriously doubting that we could construct such a node without testing it in a lab. And he was more traditional, and he didn't really believe in this power of FEA. So we had to prove to him what you can do. And we were actually taking part of our research work to prove to him where we had, tested things against simulation and testing, and kind of showing him that, we're not creating beautiful color plots in Rhino. We actually kind of know what we're doing. And this is really difficult in terms of structural design, because you have a connection which is working through friction and contact, which is something that's terribly computationally expensive to simulate. So simulating one of these nodes on a very strong computer in our office with one single load case would take up about 2.5 hours of calculating it until we got a result. So you can imagine that would have been totally impossible to check every node in the system. So we needed the hand calculation to find out which one we need to calculate, also compare the hand calculation to the FEA, so our third-party review kind of knew, okay, this is safe, and then go deep and understand the exact stresses in the system, because obviously there are some knot stresses in the corners, and you kind of need to understand what's happening there. And then when this thing came to site, we tried to figure out a way that this was also really fast erect. So what we did is we designed these connections, and you can see if you look really closely there's these kind of pins that are running through these tooth sticking out. And these are only there temporarily to lock the piece of steel in place. And you can see the top left arm is actually only hanging on one single cock that's connected to the central plate. And there's only one plate there. Later there's going to be two. So we designed the system so it can withstand that for the longest arm in a horizontal layout, so they can build it as a free cantilever. So in the end, on site, they only had 3 guys. They had one guy sorting it, one guy putting it on the crane, and the third guy adding it to the nodes. And they were building this thing in a couple of weeks, actually. On a side note, when you make a parametric model of such a connection, it's very important that on day 1, you think about the odd ones out. Yeah? So 90% of the nodes are perfect circles, but there are some situations where the geometry is so tight that we can't fit it onto a circle. So if we had scripted the node based on a circle, we would have spent almost as much time hand drawing or hand computing the last 3 nodes which don't work as we had on working on the script. But because we kind of picked these points right from the beginning, we built the script around the kind of most complex part of the geometry so it can handle everything. This is really, really important in whatever you do in computational design, that once you go into the digital, you make sure you never have to step out and do something by hand. Yeah? And if you do, then this is also an important part. All the scripts that we work with, none of them are complete runs from design to production. They're always elements. So in each element, you can export the geometry into a layered structure that you have in your CAD software. You can, if you need to, you can change it by hand and then feed it back into the automatic digital world. Also really important part, yeah, at academia, we tend to try and build this perfect loop that everything is connected and you can't really manually interact with it. This manual interaction in parts of projects is really important. It's just time efficient. Okay, so you can kind of see the result in the end. You can maybe get an impression of the complexity of the geometry. Now, once this thing was built, we'd kind of understood that this way of working with steel works fairly well. And we applied it to the next project, which was a textile facade at the new Adidas campus in Western Germany, where Adidas had this idea that they wanted to clad the big parking house in the south of their campus with a facade that's kind of triangulated, and they wanted a completely kind of non-repetitive pattern on it. So the design challenge we had was to generate a facade layout where everything was unique and you wouldn't kind of be able to recognize that parts are the same, and make it kind of fairly efficient, because this is it's an 8,000 square meter facade on a parking house, which naturally doesn't have a very good budget for an additional facade. So with a PhD from this InnoChain program, which we are part of, some of you may know it, it's a PhD program across Europe, and we are one of the industry partners. And our PhD student, Zeynep, who's working at the Angewandte in Vienna, she came to our office and started scripting these systems where, through some machine learning and different scripts, she was trying to organize a triangulated facade system that would just kind of form find itself into something that is totally non-repetitive. And we found that, we had parameters that we wanted to meet angles which didn't go under a minimum inclination, so we could build our node. We wanted a certain amount of amplitude between the low point nodes and the high point nodes. And most importantly, we needed cellular sizes which work in terms of the textile. We wanted to keep it within a certain size. And it kind of turned out, when it was fully automatic, that we'd always get about 80% of the facade to work reasonably well. And then there was always these 1 or 2 corners which totally don't work. So in this generative way, we were able to handle a large part of the project, but the rest just totally didn't work. And then when we tried to manually adjust that last bit, that also didn't work, because once you're really constrained within your mesh, then it just, we couldn't really figure it out. And we understood that maybe actually we need a new approach, which kind of brings it back to this question of also creativity, and where do we come in as designers, and where do we use automation. And we really found that when we were looking at the facade and we printed it out, you immediately see where there's repetition, and you see like, we needed like a bit more organized on that part. We have a natural feeling for this. And we were asking ourselves, what can't we implement that? Why do we even automate that? This is almost the biggest fun we have in our profession, just that moment. Why are we automizing it? So we started drawing this facade and just building bounding boxes around the nodes, and just allowed it a certain geometry within which each node could travel, so it could optimize within a system that we had kind of laid out. And this approach actually worked really well. We managed to then generate facade systems on something that we'd initially designed, and then we got feedback of optimized geometries from that. So we were kind of breaking down the system into something where we could interact as designers, because we have a very good feeling for what the geometry should look like, and how we could maybe resolve a corner where there's an opening, and then automate the system to a degree where we can then, it leads to a result of a non-repetitive pattern. So these are kind of 2 examples of the way we can maybe in some projects rethink the way we are working with steel, in the way we design the details, in the way we handle the projects when they go to site, and also in the way that we can think about the whole manufacturing process throughout the design. So one little detail about this is a glass fiber fabric, which is hugely expensive. So finally, it all comes down to not wasting material when you cut it up. So if they had clad the entire triangle with one single sheet of material, we would have, in nesting it, we would have wasted a lot of offcut. So that's why we broke it down into 3 triangles within one, which actually adds a totally new pattern to it, almost a 3-dimensionality to it, because you see the fiber direction reflecting different in the light. And also, this was kind of the prime parameter in our optimization run, that we optimized the geometry towards nesting of the textile. So this was the highest ranked goal in the optimization, was that these triangles are really optimally nested. And that kind of also talks about this way that we worked with the industry, where you have to work like this when you're in the later design phases, when it's going onto site. And often we find that we are not forced to think about this when we start with the very early conceptual design phases. And often then the most critical decisions are taken that are stopping us from doing something like this in the later stage. So as we're going towards more inclusive digital processes, and we're able to think about the manufacturing, and we're embracing this complexity, and we're building these crazy geometries, it seems to become actually much more important to think about this in the first place. So we're taking decisions that make the projects handleable on site, and then make it even possible to deliver them within time and budget. But we're not really forced to do so, right? In the way the building regulations are. In Germany, we're not even allowed to talk to the industry in the beginning, because there needs to be a kind of open tender process. That's kind of where we're at, and where we're trying to find solutions, trying to talk to industry early, And I think these are really the big challenges that we're having to handle in the next couple of years. So it kind of comes down to kind of finding our way through these new digital tools and maintaining our grounds as what we love in our profession as being creative engineers and architects, and not letting digitalization take over and make us slaves of the software that we're using, which was kind of the example in the beginning. There was only one type of system that we could construct in our BIM software, and so we're forced to do so. So we're kind of looking for the grounds of creativity within our profession. And creativity ultimately, and this is always what we promote at university, and that's what's very heavily promoted here at university too, is that creativity can also come from the material itself that we're working with, right? So you cannot only exploit the manufacturing processes that we now have available, or the software that we have available, the tools that we have available, but you can also exploit our profound understanding of material behavior and make that the design driver. And this is what we like doing at university, and this is where we're currently wondering how we can transport that into industry, because that's almost even a step further away than thinking about manufacturing in the early design, thinking about how material can influence design to an extent where it's influencing the manufacturing. So this is kind of bringing it down to, this is what this picture talks about, where much of my PhD was about how we can use straight or planar building elements and exploiting their elasticity to create complex geometry. Bending active structures is what we call it. In Stuttgart, we're lucky to have some, Kostas mentioned it, some very famous architects and engineers. When I started at university, and when Achim Menges actually just left the AA and came to Stuttgart, I had this idea of working with bending active structures. And Achim was just involved here at the AA building this hype grid shell, which is also kind of exploiting elasticity of the material. And then we said, let's do a design class together and see how students can come up with totally new ways of constructing if they exploit elasticity. And we called the class Bend It and went to Frei Otto, he's sitting at the bottom right, and started talking to him about how they used elasticity in their designs of, for example, the Multihalle in Mannheim, and they have a good book about bamboo structures where they're working a lot with this. And Frei Otto actually said to us, he always thought that was a really clever way of building, but because he didn't have the engineering tools or the engineering available to really predict what's happening, they never really dared to solidly rely on these geometries for large span structures. So actually the Multihalle Mannheim is our most amazing large timber grid shell, but the form finding on it was based purely on catenaries. They didn't really have the software or tools to base it on the natural bending geometries. So this set us off on this project. Some of you may have seen it. This was the first pavilion that we built in Stuttgart between the ICD and ITKE. Lots of students and almost as many PhDs involved. A lot of us kind of started their adventures into this computational design scene driven by material behavior at the time. And here, very early in the design process, we thought about the connection details because we were working in teams where manufacturing was a large part of the design. So we really tried to find out how can we make finger joint connections in very thin and flat sheets of timber. So we found this kind of puzzle connection that is glued and finger jointed because the timber is only 6 mil thick, so we can elastically bend it. You couldn't make a classic finger joint, it would just simply break open. So this was always a part of these kind of systems where you think about material behavior, computational tools that work on a level of abstraction. So we were doing lots of tests, actually measuring real timber arches to understand how we can abstract their geometry and script them. And then my part in the whole process was to mirror that computationally for the structural engineering side, which in this case meant that we had to re-simulate the entire erection process. So we have a model that describes all the internal stresses of the erection and can then be simulated against wind and snow loads because it was going to be standing outside. So I think for many of us who were working at the university at the time, this was really an eye-opener. It was, you know, for us the first time we used a robot. Not very challenging for the robot to just cut 2D, but we just had a robot. Could have been done differently. And you know, it was the first time we were using this methodology where, again, on site, the members describe the geometry and not the plans. In this case, even more, because you come in with a flat sheet of material, and as you bend it and lock it into place, this shell form is naturally generated. So this was, yeah, as I said, a really interesting learning ground to learn about how we can simulate these things, how we can streamline it towards fabrication, and also kind of measure their performance when they're built to a larger scale. The thing that I noticed, though, also, I'm sure many of you are aware that since then, almost every year, one of these pavilions was built, always a different material system, and also based on the availability of what manufacturing technologies we had at hand. And we kind of noticed that in these groups of students, which were sometimes up to 15 students and 4 or 5 PhDs, there was only ever 1 or 2 or maybe 3 students which were actually really handling the computational model. Now, there was lots of people involved, organizing, testing, producing, manufacturing, doing some engineering, but the actual handling of the computational model always boiled down to 1 or 2 students. Simply because it quickly became so complex that they couldn't explain it to each other anymore, and we didn't really have the tools to handle it with many people. There was just one computer. So when I came to HCU Hamburg, I wanted to set up with engineering and architecture students a way where I deliberately wanted to build something computationally that's not built from many modular parts, but as one mega structure. And I wanted to find a way how they can all collaborate within the digital model, just as a kind of test ground to see whether we can handle this with many people. So we spent a lot of time sketching on the board these kind of data trees and ways of organizing the project. At the time, Flux was still for free and up and running. So we saw that this Flux plugin was really good to split up our scripts and connect them in a cloud. So we had engineering teams, we had manufacturing teams, and we had computation teams and form finding teams. And they were all working on scripts that were based on the same data structure. And whatever outcome they would have, they would upload onto the cloud, and this data structure could be downloaded again into their models. So this little video talks a little bit about that. It's just focusing on some structural parts of the system. So we have the central information model where data tree was handling the system. And there was fairly abstract models of the system where people doing the details could just pick part of the geometry and adjust it to it, maintain them parametric so that only at the very end, in the last loop, we were updating the geometry in every model and using it on the final system. This was just one small aspect of it, which was organizing that within the space where we were hanging the structure, we had to a very set boundary condition because we only had singular points where we could attach it. And they wanted to build something where we could measure the way we can predict complex behavior. And the way the students wanted to measure it was by building 2 totally separate structural systems, which are bending active in the sense that these high points within the 2 separate systems are pushed out by elastic rods. And we wanted to measure how good we were by seeing whether the two high point circles were opposite each other and parallel. Yeah. And we had no way of adjusting the geometry because this was all fixed points in space. The whole structure was optimized so the resultant forces were all perfectly pointing in the direction where they were anchored. And then we were there with a surveying team from the university that just told us where to pull each cable. Students could only pull it from the side. So very early when they were cleaning the windows, half a year before we constructed, we just attached cables to the side and then we could just hoist it up half a year later when we'd built it. There was lots of problems with it. The material didn't work very well because we had to use fire-rated A2 material, which is super non-elastic, and it was a nightmare to produce. But the students sewed it themselves, we produced it all ourselves, and the equilibrium system worked within a few centimeters of tolerances, which we found kind of a success in this sense. So now there was this kind of floating system that talks about where we are at in computational design in terms of predicting behavior to such a complexity where you're not allowed to correct it. You actually can't correct it. Funny story on the sideline to this, there was a conference half a year later, there was a couple of wrinkles in the system, and then some students said, come on, we have to get it really nicely tensioned, and then they started intuitively pulling on the cables to kind of make it better, and that totally wrecked it. And they never found the real geometry again. So we had one corner was better tension and the other was totally off. And so that was kind of also a nice feedback, is that the best we could get was by relying totally on the digital model. This mirrors back into our daily practice, into structures where we build things which are not so apparently computationally designed, where the topology and the system that we're building is a seemingly classic membrane structure. In this case, a convertible roof in a road in Switzerland, which we had to cover, a 53-meter long road, 12-meter span, and they wanted to kind of have this adaptive space where if there was sunshine or heavy rain, they could close this roof. And it's attaching to 6 different buildings within this road. So a large part of our computational engineering was about optimizing this structure to find the support points within these buildings and find a structural layout that would deliver minimal support reactions. And to do so, and this was kind of the necessity to even be allowed to build this structure, we immediately had to work with very detailed structural models and run them through multiple different geometries. So we weren't even sure whether it was going to be spanning across 2 stories or 1, whether it was going to sit at the top of the road or at the bottom. So there was multiple little iterations between things that were almost the same, but they were not. And in this case, what we had learned in terms of connecting our structural models in a computational way to the form finding and architectural models was hugely helpful to fastly iterate towards a design that would even function within this. And in the end, I always find this really interesting, and I often get asked by students at our university if we're doing this, if we're building these pavilions, is anyone going to actually employ me? Because I don't really see the big offices building that. And my feedback is always kind of making students and making also us as teachers understand that what we're actually teaching is to handle these hugely complex processes, and we can adapt them to everyday problems very easily and make us work very efficiently. And in an ideal world that I haven't found yet, it would make us gain time for the creative parts of our profession, right? So this is the ultimate goal for me, that computation makes us gain time for the fun part of the work. This was why Konrad Zuse built the computer, right? Which I said in the beginning. Sometimes in daily practice, I feel that we're not quite there. Now maybe only I'm doing something wrong, but I'm often finding myself being the slave of my way too complex engineering model and just solving problems all the time. We kind of brought it to a next level almost of connecting design, fabrication, form finding, and engineering into one model when we built the Danish pavilion for the Venice Biennale last year together with CETA Institute in Copenhagen, where we wanted to include knitting as one of the main parts of the structural system in terms of the membrane structure that was built. So knitting today allows us to build 3-dimensional textiles without any connection seams. And we can include in a knit a 3-dimensional multi-layer textile where all the details, all the sleeves, all the connection points are actually knitted into the textile. That's what your sneakers are made like today, right? So if you look at your Nike or Adidas sneaker, you will find that this is actually totally knitted from one piece of fabric. And we can scale this up. There are machines that can knit as wide as 2.5 meters, and we can actually build some very sizable structures. So driven by this idea, and CETA has done many years of research on this, we launched into this idea for this pavilion, where we wanted to connect this world of bending active, or what we call textile hybrid structures, to knitted fabrics. And again, through multiple exercises, also purely model building exercises, try to find geometries that were completely self-equilibrating. Just like what we've done at HCU Hamburg, where all the forces are shortcut within one system, and they're totally in interaction, right? The tension of the textile is bending the beams, and the elasticity and the spring back of the beam is reversely tensioning the textile, like a complete bow and arrow system. Today, our FEA analysis of doing something like this is still terribly slow and really hard to set up an interactive process with it. And tools like Kangaroo or softwares that we are developing in our office, working on isogeometric analysis, are a lot faster. But at the end of the project, when we're handing in our structural engineering report, we can't give them a printout from Kangaroo, right? So we've had this phase in the last couple of years where actually things have become almost impossible for us to engineer, because we have architecture offices that are giving us designs and they say, this is physics-based modeling, super optimized, you basically just need to sign it, kind of thing. But we have actually no way of accessing the geometry. It's become so complex that we as engineers, and we have to calculate them with our tools, we're like, the only thing we can do is just materialize it, press the load button and see what it does. But we have no way of rationalizing the system, because it's become so complex that it's even hard to describe the topology or let alone describe any kind of typology that's sitting within the system. And on the other hand, I don't want to say that that's wrong. You know, this could lead us into an amazing new field of structural design. We're just kind of really relentlessly looking for ways of attaching to it and finding a way to interact with it. And this Venice pavilion was really all about that. So if you go back to this image, it was really about connecting. These are all different form finding and simulation softwares, which are all really good for one aspect of it. And we were really trying to find ways that they all speak to each other through central information models that were handling the project in the same way they were describing the topology, so we could translate them between different softwares. So this would be the Kangaroo model, which is super fast in form finding this basic equilibrium system between the elastically bent rod and this tension textile. But we also know from tests and from comparing it to our FEA modeling that it's not very precise in what it's predicting in terms of the final outcome, because it can't even show the system under dead load. Yeah, it's just showing the force equilibria between the pre-stress of the textile and the spring-back effect of the GFRP. But actually, these hyper-elastic systems, they're actually already under dead load. They take on a different shape to the one that we're simulating. So in this case, we can start using softwares like this isogeometric modeling, where we're performing FEA not on meshes, but on NURB surfaces and splines, which is making the parametric model very easy, because we don't have to break it down into meshes. And we can, you know, already, once we know where the geometry is going, use this currently still slightly slower way of simulating it, which can already give us feedback about wind forces, about dead load forces, and all of this. Finally, at the moment, I don't know how long this is still the case, but at the moment, at the end of the day, Venice Biennale, super strict third-party review. You have to hand in a Eurocode report on something like this. So you have to at least be able to show them that you're using a conventional engineering software by which you're simulating it. And we've worked a lot with this one FEA called Sophistic, and we actually promoted this bending active world so much to them that they have implemented a new beam element, which is now allowing us to input a curved beam, and then Sophistic back calculates the internal stresses. So we don't anymore have to start with a straight beam and say we're bending it into a shape, but it can back calculate from the bent shape what the internal stresses are, and then relax it into the final geometry. So now suddenly industry has come along with us, even just on this tiny detail. And we did some research together with them, and they just thought it's a nice little challenge on the side. It has zero impact for their industry, but in terms of computational development, it was a nice sideline for them. And now suddenly we have this tool where we can directly connect our FEA model to the Kangaroo model, because we no longer have to repeat the form finding process. We can just pick it up and make it a little bit better. So already we're like a tiny step towards something that is a little bit more inclusive. yeah, and then in the end you see this the system, which is really there was a large body of work by CETA about controlling the knitting patterns that are involved in this. I'm only talking about the details that have to do with the form finding and the engineering of it. Maybe one little detail, you can see this on the picture on the left. It's not very clear. You can kind of see these axes on the, yeah, you can maybe see this, and this has a different color to this. So this is basically changing the knit, and it's making the knit slightly more elastic towards these high points, and that allowed us to pull out these cones without a cutting pattern. Yeah, so you can really differentiate the elasticity within one textile. All right. So currently this has taken us to the next exhibition, which is the World Expo in Dubai, where now we weren't involved from the starters, and we're again at this point where we get asked to rationalize a system at a later stage. And this is actually a super interesting story about how this project came about. This was a competition that was won by two students, or PhD students from the University of Prague, that have formed their own architecture office for Mosa. And they had this idea, they want to exhibit a kind of a water recuperating system that works in the desert. So it's a kind of complicated plumbing and spring system. And they wanted this entrance installation as a shading canopy. And you can easily imagine that if you show this to a kind of a structural engineer, especially in the Emirates, you know, they're just going to say, forget it. And so the first engineering approaches towards the system were a kind of steel frame structure of which you hang the tubes. And a company approached us and said, don't you guys have an idea how we can build this a little bit more efficient? And obviously, you know, when I see something like this, I go like, bending active, let's bend this whole thing and build it like that. So we had some really cool workshops in Prague with these architects, and we actually just built models with them. So we could, you know, transport our ideas, and we could show them and also ourselves understand what types of geometries are possible when we are building something like that, where the aim is again to build something that's seemingly chaotic, totally interwoven, but we have to find within that an access towards something that we can structurally optimize without making this thing look like it's a fixed typology. So it's a kind of really cool challenge. We're trying to build something that has some shell performance without making it look like a shell. And to do something like this, really the best way is just to build physical models, because you can immediately see what the feedback from the model does. So we've built, I think this is the third model that we built together with them. And then we actually mirrored the model building computationally, again using kangaroo scripts, where we did exactly the same. We found that if we were to build, this is over 6 kilometers of GFRP that's going to be in this canopy. And if we want to build this within like a time slot of a month, we can't put every single rod into the pavilion by one. So we already said we'll cluster them by pairs of 5. So you have these strips of material, which we started working with in the model building, and could also prove that these strips in their interlocking work really well structurally as well. And so we set up a system that we wanted to have these strips that are folding back in on themselves and generate geometry through that. We were describing the topology of what we were building in the model, and could then mirror that back into a computational design system, which we're now, with these new beam elements and FEA, can seamlessly translate into our system. So there was a lot of manual work involved, a lot of thinking about how to set up the project so we can describe it based on a topology, just based on a mapping system, so we understand where we are within our model, without breaking it down into something that's symmetric or kind of easily readable as a system. This is where we're at now. We've just passed the approval of conceptual design. The next round with the expo is going to be a little bit more difficult, because now we're down to all these fire rating issues, so there's still a bit of mileage to be done. But it's really in this project that we're bringing together now in a commercial project everything we've learned at university, at these collaborations with the university, and now kind of starting to be able to connect all of this into one world. And then the really funny thing I always find is when you kind of shoot out standard architectural drawings or something like this, and you make standard elevations and it looks just like totally way out. Then I think this has kind of been worth it. Again, talking about scaling up these ideas to building structures where we can actually make a significant difference about the masses that we're building today. My partner at the office, Alex Michalski, he's done his PhD in wind engineering, simulating natural winds. And we have set up in our office a big cluster computer where we can now simulate wind in coupled CFD and FEA models, something that we call fluid structure interaction. And the way we're using it now, actually quite a lot, also simulating for cities, is the impact of our designs in terms of the thermal comfort, in terms of the wind and the fresh air access to cities, of what new buildings have in terms of impact in our inner cities. And also we find that especially when we're building high-rise structures or more complex bridge structures where we have to rely on wind tunnel analysis to do our structural analysis, because in more complex systems, the Eurocode or whichever other code doesn't give us the right wind loads for these shapes, so we have to give our designs to wind tunnel. And we find that by that time, we have already pretty much fixed everything in our design. Yeah? By the time the wind tunnel is doing their tests, we are in the later stages of our design where we can never go back to completely changing the shape of our buildings because we're suddenly finding that it's not performing very well in wind-induced vibrations, or maybe it has a bad impact on a neighboring building. So on this front, computational wind engineering is really important, and especially important in this case to connect it again to the design environments. So there has been CFD codes out there, and people have done so, but it hasn't really been possible to include it into a design methodology where you can really rather quickly work off feedbacks. And have this all based on a system that is proven to deliver results of some precision. These final stages of modeling, what you're seeing here, is where we've connected our data to wind tunnel data and checked the correctness of our results. And then with this, you can then go quite far into the analysis of how the wind interacts with the building, because now, as our tall buildings becoming more and more slender, wind-induced vibrations and the dynamics of these structures are very difficult to handle. So we are having to either face these problems at a very late stage in our design, where we can just simply add tuned mass dampers to the top of our high-rise structures, which are very expensive, or if we're somehow managing to include this analysis in early design, we can try and lay out our structures that they are still as slender, but somehow perform better in terms of their dynamics. So this is kind of another access that we're finding, is that setting up our connections of our commercial engineering tools, connecting them to all parts of the architectural design, is enabling us to also on that front include these design ideas. And then finally, we're kind of left with this question where, usually today architects and engineers like starting their presentations with these kind of graphs. In the next couple of years, we're going to hit the 9 billion, and now in Europe, where almost 80% of the people live in the inner cities, and this is a huge pressure, and how do we find answers to that in architecture? I'm showing this at the end, because I think these are questions that we're having to answer, and I'm very aware of the fact that none of the projects I showed you is able to answer any of these questions, right? Because we are working in fields where we're working on special structures that are often the highlights in an architectural context, and they're not building the mass housing that we need. Maybe in some parts, this wind engineering can answer how we can build tall structures and how we can build them more efficiently. But we, with our work, are not really able to answer these questions. And as I'm very aware of it, I want to show you a project which we're working on at the moment, which is kind of looking towards directions where we can, bring in our creativity in structural design into some questions that we are being faced with, especially in Central Europe, quite a lot. This is a freeway that's bypassing Stuttgart, And at the time when it was built, it simply cut one of the satellite cities to Stuttgart, just simply cut it into two. And if you see at the bottom right, you see this large green. This is actually a school. So they're right next to the freeway, and the city is just cut into two cities. And there's hundreds of places across Germany and Europe where cities and communities are really putting a lot of pressure on politicians and saying we need to put a cover on the freeway because the sound emissions, the CO2 emissions, and the way this is cutting our communities within cities apart are just unbearable. And politics recognize this and say, okay, we'll put it into our master plans. And in our master plan in 30 years, we're anyway planning to make a 4-lane freeway out of this. So in about 36 years, we'll come back to you and we'll look at this problem. Yeah? And you actually really find a lot of cities that are having to deal with this. And in this case, it's even more complicated because the freeway is state-owned, and the city and the bridges, the city owns the bridges, so it's kind of politically also really complicated to find an answer to this. So there was in Germany we have a council of lightweight engineering that was made aware of these problems, and they asked us whether we couldn't develop some solutions for that. And the way we approached this is we first looked at the traditional ways of building covers across freeways, which is always a type of tunnel construction. You build a kind of fully enclosed lid, very expensive structure, and especially a huge pressure on the freeway because you're having to close most of the lanes while you're building it. And the whole financing of it takes really long because no one really wants to pay for it. So we had this idea that we could build something that is actually bridges that are spanning across the freeway, and we would build the bridges so they're load-bearing enough that we can build houses on them, so we can resell the space that we're building over the freeways. And in between the bridges, we'll build something super light that makes the cover. So what you're seeing here is in the center, you're seeing these steel bridges that are shooting across the freeway. We can actually build them also 30 years before they make the freeway with an additional lane, because this is anyway what's being done. If you see most freeways in Germany, they always have a lot of space on the side because they know at some point we might build another lane. So there's anyway this tradition that the bridges are spanning further than they may need. And then in between, we've developed, together with some specialists in botany, we've developed a system where we have a cable net spanning in between the bridges with a geotextile on it, and then extensive greenery growing very lightweight on these surfaces. So these are merely covering the freeways. We could eventually also build them that you could step on them, but not add significant load. But what we're doing, we're building the cover as bridges, and we're kind of spanning in between. So this is kind of what we understand also as a hybrid approach to a system. We're not building a bridge or a tunnel. We're building a hybrid between kind of tensile membrane structures, bridges, and parts of tunnels, and kind of mixing all these worlds together to find eventually new solutions which can answer these problems and include that already in the layout of the existing bridges that we have there present. So this is a project that's currently running. It's very present, obviously, in the media because there's a lot of people who want this and a lot of people who say it doesn't work. And we're kind of in this debate right now where we'll take it next. So I want to conclude with this quote by Bill Baker, which I find very fitting to our time, where he says, in the past we were limited by the computational power, and today the problem is how we harness it and use it wisely. And these are questions that I can't answer, but I can say at least that we're aware that there's these questions out there. Thank you very much.
I'll maybe start off with the first question and then I kind of leave it over to you. I think it's very interesting the fact that you start off with each project with showing a detail of kind of how things come together, then from that go into larger forms and the whole building. And you were talking a lot about efficiency and kind of streamlining the process and you know, trying to kind of embed intelligence in the actual kind of detail and the component itself. But for me, like quite a lot of maybe the inefficiencies potentially come from this kind of very old kind of condition of having to design in 3 dimensions and then having to, from the 3 dimensions, cut pieces down and then reassemble them on site. So you go from 3D kind of information to 2D that is then numerically maybe kind of like an index, and then from that into kind of building construction. But then in, for example, and this is kind of the case with architecture, that it always kind of potentially lags behind other industries as well. In other kind of disciplines, you have this thing that somehow kind of there's this idea of components merging together and actually becoming one piece, and even the materiality of it being kind of targeted to be, you know, consisting of bi or, you know, even 3 or 4 materials. So how do you see this kind of potentially evolving? Like, would you, because already there's, you showed you went from 2,920 connections to 260 bolts, and then reducing kind of weight even more. Would you think kind of the next, like, let's say, you know, like step in that would be actually to fuse these kind of components and look into more integrated kind of ways of constructing, and also kind of going from design into construction directly without having to cut things down?
Well, I think this kind of summarizes exactly the questions that we're asking ourselves. There's, in terms of fusing components, there's a project that I didn't show just because it didn't fit in time-wise, but it's just as important, where, you know, with these kind of cog connection systems, you can't solve every problem, right? There's some geometries where you can solve it fairly well. And we've had other structures where it just simply didn't work. And we've learned that today casting steel is actually something that we can really efficiently do again, because we can 3D print in sand the molds. So we had a project 3 years ago where apparently in Europe we were the first company doing it, that we were printing the molds in sand. At least that's what the manufacturer told us. But I think in the car industry it was already kind of present. And it's now coming into industry where we can use it on a larger scale as well. But it was totally amazing to see the results of it. I mean, obviously the form of a cast node is you can build almost anything, and it's super beautiful because you have these seamlessly connecting lines in your system. And it was actually very cheap. So no one wanted to believe us when we said, let's cast the node. Everyone said, no way, way too expensive. But because we can include digital manufacturing in that, in building the unique dies to pour the metal into, this makes it efficient enough to actually make it, in the end of the day, it was cheaper than welding a complex node like this. But what's behind it is actually just in the same way that we had to deal with it in these laser cut parts, we had to deal with it in these cast steel nodes. There's always a large part of education almost that needs to be done, and convincing. Because the first reaction is always, you look at it, you don't know it, way too expensive, way too complicated, we can't do it. And we've really learned to explain that our solutions are complex and not complicated, right? And this is actually a huge difference, because complexity can really be handled computationally. And it's actually very complicated to weld something and match the geometries exactly. So this is kind of the debate. And for us, we've really found that all these questions kind of boil down to complexity versus complication, and making a difference there. And at the end of the day, I mean, we've had to run in many walls and had many throwbacks. And at university, we always teach the students it's super cheap to laser cut something individual. It really doesn't matter that every part is different. Forget it. In industry, the laser cutting industry is outsourced from all the steel manufacturers. They are in a terrible cash battle to get machine hours to sell them. So the machine hours that they're selling between all the different laser companies are almost the same, and they keep lowering in price. So the only bit where they make money is in preparing the models. So when you get a price from them and say, okay, we need X amount of kilometers of laser cutting of 15 mil steel, then they say, yeah, it costs so much, and then you send them the models and say, like, these are all different parts. They're like, yeah. Well, we need to open every file and check it and prove it and this and that, and then suddenly the price triples. And then there's no way that you can actually overcome this, because this is how they make their money. So it took us months to organize that you can make that efficient.
But I think that's interesting, because actually it is not that they can't do it, it is how they make their money,
Exactly.
right? Because I'm also thinking, when you're saying, like, maybe it's actually really good indeed to make them super expensive and all different, if there is like some catch on the other side. So all the other elements are the same and super cheap and handleable by people, right? Because I think great lecture, but also thinking about like the power of computation is one thing, but also I think the power with that to allow us to think differently, I think that to me is actually the best kind of opportunity. So indeed, like, how can you kind of make a balance, let's say, between this? Because, yeah, I'm not sure if this is how I'm going to phrase the question. So let's see. So let's say we have computation on one side, and on another side in your presentation you also said that, you know, you kind of lost the feeling, because actually you can compute everything. So you're a true believer of whatever you compute. But we can compute a lot of things, and even if we cannot kind of, let's say, go back to our hand calc, how do you find a balance within that? And one thing is the balance, but also I wonder where in your practice lies the opportunity. Is it in the ability to verify something different, or to compute differentiation, or where does the opportunity lie? And how do you feel about the really big difference between hand calc and real feeling and understanding in your heart and in your hands versus believing of whatever this mega computer tells us?
So there's obviously no one answer. So actually, the opportunity, I said this quite openly, and I'll say it again, I don't know where this is leading us. I don't know where I very honestly don't know whether this is making our profession more fun. There's moments where I don't know it, right? There's moments where we're so tangled up. There's a lot of moments where we're so tangled up in resolving the complexity and understanding it, where we're spending massive amounts of hours on kind of dealing with what we've done. And where I'm really often saying, like, we are so stupid as a profession to always, now we have the tools that we can automate everything, and we're not using it to automate the things that we could do, but we're using it to, like, push it a bit further, and no one is paying us for it. That's kind of the dark side, or the very, very kind of almost comic side of describing it. Obviously, there is a lot of opportunity in it, and there's amazing moments where you find that through these tools and through connecting them, you're finding a new way of collaboration. You're finding that the tools actually make you collaborate, make you communicate, and we're finding that we're really sharpening our skills in communication. And we're finding that it's actually leading us more into model building and into hand sketching and into hand calculating, to discuss our project kind of on a different dance floor than we process the project. So these, I find, are the real opportunities, and this is kind of what I hope we gain more time for. But I can't say that we've at all won the battle.
Yeah.
In terms of your company, I think that compared to other companies, or to, let's say, the generality of all the engineering firms, you are quite innovative, let's say a lot innovative, and you did a lot of research, probably as a personal people, but as well as a company. But which is the added value that you can give to the projects with all this innovative process and this research? So not only what the clients can understand that you're giving value, but as well the project itself.
Well, I mean, The place where we come from in Stuttgart is this idea that lightweight structures mean that you're optimizing towards an inclusive system. Lightweight structure, the very basic principle of lightweight structure is that you don't use lightweight materials and then you say it's lightweight, but you use something which serves multiple functions, and thereby, by including functions and by including geometry, by making form and structure one, so this is kind of our highest goal always, making the system more efficient. So ultimately we do see, and we get this feedback a lot, that we're saving an awful lot of material. And this is, I think, a very important goal. And by including material behavior in this context, we're not saving material because we're cutting it away or because we're milling a complex section out of a solid section or something, which the car industry does a lot. So, you know, you use topology optimization and then you build this new axial. That's, in our sense, in the building industry, it's not really saving material. It's taking material away, making it lighter, but we've used the material. So using material behavior, using initially flat parts, which are very cheap to produce and cheap to ship, and then building complex geometries out of that actually makes a very measurable difference in terms of how much material we use. And this is really what's pushing us.
Just one thing. And do you think that the optimization of the material, because of the structure and, let's say, the shape or the form that we're doing, I understand that it's very interesting itself, but sometimes all these, let's say, structures or these buildings has a behavior with, let's say, an MEP or lighting or comfort or a facade or the space itself. Sometimes the optimization is going against two other disciplines. So how you link these things with other disciplines? For example, thermal mass. So as soon as you do a light structure, very interesting, very nice, super optimized, but then appears the MEP guy and said, I need thermal mass. What happened with it?
I'm realizing that I put the title to the lecture, but I didn't explain it, because this is why I called it New Hybrids. So you mentioned that we have this legacy in Stuttgart of these engineers like Schleich and Otto. They were performing a lot in the 90s and early 2000s, where a very technology-driven design was en vogue. So there was a large acceptance for large span structures where you can really read the structural system. So it was actually almost a much easier time for structural engineer, because we could go with these super clear typologies of structures, and you could really make a fully force-driven design. Today, because we have much higher pressures from the building physics, we have much more complexities coming into the system, and we have much less acceptance for these kind of pure structural forms. We can't work like that anymore. Yeah, my older colleagues were still working in a time where the engineer could say, we build exactly this shape because that's optimal. I've hardly ever worked on a project where we had this opportunity. And so the answer to that is to find hybrid ways of modeling the system, hybrid in the sense that we're including multiple materials, multiple design environments into something where we find kind of almost like compromises, but compromises in a very positive sense. Because a compromise is inclusive and it's not additive, right? And we're trying to not go down the road of just saying, okay, we're lost, we're just gonna put in our structural system and then you add whatever you need. A compromise in that sense, I still find a higher goal, because it's inclusive in that sense.
And do you see also like this complexity that you're referring to on a material level itself as well? Because I mean, from my kind of own research, and I mean, I'm coming from a different background to engineering, but when I try to ask people about this, about actually trying to use kind of materials that are not uniform, not isotropic, that they go beyond just alloys or a single material, always the answer was that, you know, like it's a very complex thing to even calculate on very standard kind of forms as well. So do you kind of try to work, or have you seen kind of working with much more kind of diverse forms of materiality within a single piece, or as opposed to kind of multiple materials as different components that are isotropic.
There's kind of boundaries within which we can exploit that in industry, because we're only allowed to work with material behavior that's written in the code, or we have to test it. In membrane structures, there's no codes, and so we always have to test it. So there, the membrane materials, the woven ones, they're actually very anisotropic, because there you have the warp direction of the fiber, which is much stiffer than the weft direction. You have different coating systems, and you even have varying behavior across one production of material between the beginning and the end. So there's a lot of, naturally in this industry, there's a lot of testing involved. We always have to run these tests. And so we can exploit much more of that special behavior as well, because that's just part of the industry. Not at all to an extent how we're discussing it in academia, though. Because simply we're, these far ends of exploiting material behavior are usually outside of the behaviors that we're using by code.
But I think an opportunity there is like the opposite of what you said before, right? Okay, one factory doesn't want to cut all of them, let's say all sections in a bespoke way. He can do it, but he doesn't want to. But you need to find actually fabricators that are actually interested in that product for themselves, because then they want to do everything to change all the machines they have in order to collaborate and to challenge the code, right? Because indeed, testing costs a lot of money, and we all know that in our industry that kind of is a really, clear kind of limit. But also, for example, that's why I think actually working with kind of pavilions or something like that, where you can actually put something in the real world, although even if it's once and for 2 weeks, it doesn't really matter, because actually that, again, enriches the industry to think and to see, okay, it's not so difficult, we can actually do it, there might be a market, right? So, and I think actually that now we have so much more power to not only compute an isotropic kind of material, but also try to understand its behavior. And maybe I'm not so much into the whole kind of computational stuff, because I always think like it's good that we understand something from the heart. But actually, if we, for example, using Kangaroo, you can really live kind of see, and if you push and pull, okay, you can kind of see this kind of behavior, which almost is like, kind of doing that. And I think that is maybe the difference in defining typologies versus understanding a behavior, right? Because if I can clearly understand the behavior, I know, what is happening in one point. So maybe we just have to kind of find fabricators that are keen to be on our side, let's say, to drive that.
Yeah, and we find they are out there. They're just sometimes difficult to find.
Yeah.
Sorry. Did anyone want to respond to that?
One question
maybe.
The general buildings that we do is for people, and we use it. I found out that nowadays you can optimize a lot the structure, but at the end, the structure cannot be more optimized because you need to comply with some comfort. Okay, the comfort, let's say, vibrations, accelerations, or whatever. So at the end, the sections need to comply with that. Can we afford this comfort nowadays?
Well, I think we have to, and I think I actually don't agree that we can't optimize without compromising comfort. Because there's a lot of structural optimization that's not visible. The low-hanging fruits are picked. There's not going to be a massive gain in that, and we're not going to suddenly live on curved floors because a catenary shell is so optimal, and some kind of topology optimization tool in Grasshopper has told us to cut the hell out of our building. Our beds are going to be square for still some time, and we like walking on straight floors. So that's why I'm saying the kind of low-hanging fruits are picked. There's an end to optimization on that front. But there's a lot of stuff that we can optimize with the way we build it, with the way it's also a structural engineering challenge to optimize towards prefabrication, to optimize towards how much steel we use within one section. There's a lot of hidden things where the ceiling will still look exactly the same. It might still be a 25-centimeter floor slab, but what's happening on the inside, what's inclusive in terms of any MEP, together with the reinforcement system, all of that, there's still a ton of material to be saved. And we're actually finding that right now, and I think this debate is only there for about 5 years, 10 years hopefully now, where young engineers work with 3D models, and we build models that calculate the whole structure at once. A lot of our proof engineers work on 2D models where they cut the buildings into sections, and they find different force flows through the building that we find. So what happens is we make a reinforcement layout. The proof engineer finds a different force flow, makes his reinforcement layout, and these two just get overlaid, and we build the two. Yeah, this is kind of what industry does. Because the proof engineer, there's this tradition that a proof engineer just adds reinforcement bars where he thinks we should add them. But we're not building his model or our model, we're building both. Yeah, and this is actually happening across industry, across Europe. This is not like an odd thing.
Nobody actually is sure, we just double size everything.
No, it's not that we double size everything to be safe, but this is often, by the time reinforcement drawings are made, there's a huge time pressure. If the proof engineer says we need to add something, it's close to a catastrophe. But it happens all the time, so this stuff just gets added. So on that front,
that in Spain doesn't happen.
you just leave both away.
Maybe we just add some scaffolding after.
So these are kind of the industry secrets, right? All recorded.
I have a question since the microphone not working. It wasn't my fault. You ended your talk in saying we have a lot more computational capacity. No, you have a slide that said something like that. But yet you're still focused in getting the lightweight, the lightest, the thinnest, etc. And also not in terms of physics or structural, even material, but also the expression of the building. So I would like, for instance, to compare this kind of work to, let's say, for instance, what Eliza Andersek or Gilles Wrightside are doing, in a sense that they're using this actual increase in computational capacity to compute more data in terms of particles to produce some kind of aesthetics and new types of structures, which are not based on old paradigms of lightness, but actually even excess. But that incorporate things that, for me at least, are important, such as aesthetics or production of effects, which go beyond just proving optimal modernist forces or paradigms. So where would you say that your practice would go once that you have proven that you can do the lightest, the thinnest, the cheapest, even though now we learned it wasn't the lightest, the cheapest, the thinnest?
It's kind of the same question as earlier on. Where I answered that we're kind of looking for this hybrid approach. So if you compare our work to the work that was done in the tradition of Stuttgart 20 years ago.
But if you compare it to the future.
Sure. We are already not at all dictating design by saying this is optimal and this is the only thing we can do. So we're actually really interested in this conversation of including structural intelligence into something that's not purely structurally driven. But I do believe that we have a responsibility to be careful with our use of materials, especially in concrete structures. I mean, we have recently learned that we have no resources worldwide to rebuild the cities of Syria with concrete.
Correct, but
right?
I think that
so
architecture...
there's a kind of pressure that we should include these ideas. But I'm very aware of the fact that it's probably not very optimal in any sense, in a social sense or in a building physics sense, to just take out as much material as possible.
No, it's
but it can be part of the...
Beyond the optimal. There are other parameters, for instance, maybe closer to architecture and not to engineering, which I don't actually like to draw this division, but...
Yeah, I was about to say, don't draw that division.
No, exactly. But nevertheless, in traditional senses, in traditional divisions or disciplinary divisions, for instance, how would you incorporate issues of ornamentation or effects or even aesthetics, which usually and traditionally have actually depended on non-optimization devices? Maybe they allow for certain excesses at the expense of producing beauty, which cannot numerically be defined. Yes, sorry.
I think your question is actually a lot less provocative than it sounds, because I think it's exactly what we need to do, and it's exactly the responsibility we have, is to understand that we can't, that I think no one of us can force their discipline and make it rank higher than any other, because we have these multiple influences on our systems. And I showed you a project right in the beginning at the top left, saying this is the first project that we worked on in Saudi Arabia, these umbrellas. And there we actually had exactly this, this question, because these umbrellas, the membranes are ornamented, and this was done by expert in Arabian calligraphy, right? So we were...
You didn't say that.
I couldn't say everything in barely an hour. But there, just one detail there, we had a really beautiful debate about connecting the ornaments to what we anyway needed structurally. Yeah. And we found super beautiful ornaments that were reinforcing the textile in places where we needed to reinforce it. So there's ways of also having these debates. And this is, for me, this was always the best part of being a structural engineer, if I could have such a conversation. This is what I've totally thrived off throughout my profession, especially if I talk to someone who've never talked to an expert in calligraphy. How cool is that? And that's exactly what I would answer to any of these questions. Like, bring it on. Let's talk, and let's see how we can, find new solutions.
It would have been nice to see.
I can show you later.
No, honestly, it's not a bad intended comment. It would really, I think the relationship from calligraphy to geometrical forces or structural forces would have been really beautiful.
Well, I have actually a lot of thoughts, and for example, one of the things that I believe is that although computers are getting faster and, let's say, somewhat cheaper than before, and everybody can have a computer now, I think as architects we yet actually don't have so much computational power, because, for example, just Grasshopper can get fairly slow very quickly, because it only runs, for example, just on one core of your computer. And then, of course, if you're trying to program something by text and you're actually trying to run the routine and all the cores of your computer, can also be quite challenging. So I think the computational power that is available today is, of course, humongous, and it's growing every day. But we cannot, as architects, probably just very few percentage can actually take advantage of that computational power. So I think we're still kind of slaves of the advancements of the tech industry. And I don't know if that is bad or good, but probably using the word slave is maybe a little scary. And also I think towards the question that was asked before in terms of how can you embed aesthetics, right? How can you think about aesthetics? Well, I think, of course, being able to program and, let's say, embed some sorts of local rules on, right, and structural behavior or material behavior, I think it alone already creates its own types of aesthetics, right? So, for example, I mean, we already see many examples like in nature, like in bottom-up systems, like classical, like a flock of birds or ants, right? Those, they work on very simple rules, and then they create, let's say, a global order, or let's say, no, and it creates its own aesthetics. And the other thing that I really like to think about, but I think it's kind of complicated, is that we have already, I think as a profession, made a vast improvements in terms of, let's say, computational design, I would say, after the 90s, early 2000s. Of course, like the special modeling group of Foster's has proved that, or it works in Saha Code, or for example, what you showed us today, right? That we can easily rationalize structures, or let's say pre-rationalize. So it's not like from the early 90s, we model something in Maya and then we have to build it, right? So it's post-rationalized. So I think now, of course, we have the ability to be smarter with these tools and pre-rationalize designs, understanding how forces travel through structures, etc. Of course, advancements in computer graphic understanding meshes and all of this has been a great, say, contribution to, or has been something we can take as architects. But I am always asking myself, like, okay, what's, for example, the next step, right? And of course, with robotic fabrication, I mean, also, I think it's well proven. And I think now when people say, oh, such thing is going to be built by robots, well, I don't think a lot of us are still very amused as before. So, I mean, what's next? And again, like as architects, we're not in control of this, right? Like everybody's talking, for example, now about machine learning, but machine learning has been discussed like more than 50 years ago, right? And we cannot really innovate still in the technical part of machine learning. I mean, it's impossible for us.
I'll interrupt you at what's next. Yeah, I think I like being very critical with myself and with the things we do, and I think I very openly said that we haven't really even resolved the now to really profoundly understand what's next and what are the next opportunities. And you mentioned one thing, that only a part of the architects can actually exploit the computational power because they have the education to program by themselves and use the computers in that sense. And that was, I think you said it, that we should build these pavilions to kind of push the industry and push our ideas. And I think this is exactly what we can do, what you can do in academia and what you can do in practice is build the things and build our visions so that the computational industry, Autodesk, Tekla, the big industries that are producing the softwares that we're doing, that they even understand how we want to build. Because what they're doing right now is they're doing an automation of traditional building styles.
Yes.
Right? And if we are not the ones that can program ourselves, like we did in some of our structures, the systems that we want to build, then we are left with only being able to build what the software can do. And this is actually a terrible status quo to be at, right? That we have all this opportunity, and the software doesn't automize that. It automizes the kind of more traditional way. Whilst there's nothing wrong with traditional building technologies, and there's a vast amount of buildings that are very efficiently built like that. But if we want to push a little bit towards, new freedoms and new grounds of connecting all of these boundary conditions, then the best way we can do that is give the industry the images, the examples of what we can do, and show our visions. In that case, it's really not enough to talk about it and criticize it. We have to knuckle down, build it, and show it, so there's these visions out there.
There is another thing that probably is very, very interesting, which is how not to move from what you said, from 3D to 2D and then again to 3D, because at the end we'll be talking that it's 3D. So nowadays we are too much used to use plans, and probably you need to think in another way to represent what we are doing. There are some construction companies, some contractors that they now work with 3D models in iPads or things like this on site, in the same site, but it's a very few number.
Any other last question?
Hey, a question about the project you worked on previously, the effective thing. I was just interested in what you thought the role of computational fluid dynamics is in making responsive structures, and has there been much kind of backlash or kind of resistance from industry to implement weather-resistant or weather-adaptive structures?
So you're mentioning this Flektoven project, which I haven't actually shown today, the research on these kinetic facades. That was part of my PhD, and we've actually only ever built 2 structures out there that actually show this. This was the One Ocean Pavilion with Soma Architects in Yosu, and which implemented these shading lamellas based on active bending. And then we built something at the International Building Exhibition in Hamburg, the IBA, in, when was it, 2012. This was always something that was really pushed by my professor, Jan Knippers. He always really wanted to push us towards industry for exactly this reason, that we have to bring the things out there and we have to prove that we're not just, coming up with things that have no relevance. But we have found that it's a very, very hard battle to fight, to find the industry partners that take the liability to produce it, just simply because we as planners, we can be responsible for the stuff that we plan, and the industry partners, they have to take at least some responsibility for the things that they build. And if you duplicate that by the thousands of square meters on a facade system, it's very hard to find the partner, because there's hundreds of projects out there of kinetic facades that worked for 2 years, and everyone knows this. So particularly towards that, it's a very hard battle. We have, obviously, I mean, the stuff that we did had some media echo, and we still get asked at the office, every other month, there's a project popping up, couldn't we do this? And we're not bringing it to the site because at some point people just are too scared.
Can I say something to that maybe? Because I'm lately also thinking about, because we don't do any more one-off only. Actually, we are thinking also as engineers much more as like kind of product designers. So if we talk about liability, and if we actually replicate it on every tower possible, then maybe all the investment we are going to do in that one product to do something has a potential, to actually come to the real world. And I think as well, like, this is super difficult to, kind of imagine and to find out who the right collaborators in this sense are. But actually, so I think that if we move away from the one-off, there's another, possibility that we can thrive for to actually implement, the things that you guys are talking about. Yeah.
Well, which comes down to modules nowadays are not the same, but they're a system that you can repeat in different geometries, which is kind of what we're doing there.
Cool, thanks.
Last question?
I like it, cool.
I am from Saudi Arabia, and whenever I visit these umbrellas that you have shown, I just feel fascinated about how they open and how do they close. And I really thank very much for that, because it was really, really nice to do that in my country. My question is, you use different materials, but you get limited with some materials, so you need to use other materials and such. Whenever you use a new material or try to use other materials that you haven't used, do you have to have a lot of amount of information about this material to build with it or to use it for what you are using? And is it better to use different materials or rather focus on one material and be specialized in this material construction?
So there's again these kind of limits that we have in the industry, like new materials, as we may be discussing them here, don't really exist in the portfolio that we can work with in structural materials. Like we can use steel, aluminium, timber, and concrete. And then there's membrane structures which already need testing and fiber reinforced plastics, which are also not in a code. There's a Eurocode coming up in about 2 years, but right now we also don't have a code. But beyond that, we can build with clay, and there's kind of examples for that. But sure, I didn't mention glass. Sorry, yeah, exactly. But there's not a kind of totally crazy new material that we can suddenly build with without really extensive testing. In terms of working within this portfolio of materials, you'll find that especially the smaller offices or the teams within the larger office, they usually focus towards one material, because there's attached to just the knowledge about how to calculate with this material. There's a vast amount of knowledge in the construction principles that are attached to one material. So if you're an expert in steel and you know all about the steel connections, then you may not know so much about timber connections also. In our office, we try to use every material and try to have one person connected as an expert to every material, which is very difficult to do, because there's just so much extra knowledge in terms of construction, not so much in terms of the calculation. That's relatively easy. But there's ways of using reinforcement bar, there's ways of detailing steel which are not written in the code, which are just experience and maybe published here and there.
Okay, thank you very much.